Welcome to Computer Networks. This is lecture 14. We have homework 6 due this week. So it seems like some of you already finished at least part 1. Who finished part 2? Why not? Oh, you finished part 2. Okay. And how about part 3? You finished part 3. So do you want to say anything, any comments on part 2 and part 3 that might be helpful to others who haven't started those parts yet?
Actually, I barely remember. I did it last week, but part 2, is that the one where you have to communicate how many were connected?
Yes, you need to communicate that across the processes.
Yeah, I just used the same method that I used for the other one we wrote, where we had to communicate across the processes.
Which is, do you use shared memory or?
I had one implementation of shared memory, but I was having some kind of problem. I didn't feel like tracking it down, so I just started reading and writing to a file.
Okay. All right. So there are various ways in which we can have these processes communicate to each other what the rate should be. And there was a student who came to the office hours, and we also discussed various ways. You could use shared memory. You could actually do socket communication between the processes. Anyone tried that? No? Why not? Kind of gets complicated, actually, right? But you could have a well-known socket on the parent process, on which the parent is listening for messages from the children. And then the children just communicate to the parent using that socket. You could do that. And the easiest and the dirtiest way of doing this is by using files. That's a perfectly fine way for various processes to communicate with each other. The only tricky thing there is if you have multiple processes that want to write to the same file, you have to be careful. Right? So there are two types of communications that need to happen. One, let's say there is a new client that connects to the server, then the server needs to send a message to the rest of the processes saying, okay, there's a new client here, you need to reduce the rate. That's one type of communication. Another type of communication is the client, when it terminates, it needs to tell the server somehow, right? And when a client terminates, that the server needs to, first of all, realize that, and then send a rate update message to the rest of the processes, because you need to up the rate, right? Okay. So homework 7. Okay. Any other questions about homework 6? We can have more discussions on the discussion board as you make progress. Okay. Homework 7 will be due on a week after spring break, or the week following the spring break. The description is not up, but let me just give you a preview of what it will be. So you're going to implement this protocol called Routing Information Protocol, RIP. It's a distance vector routing protocol, very simple, like what we discussed last time. So there's going to be two components. So the first week you'll implement forwarding, which is you receive a packet, you need to look up on the table that tells you on which interface or to which next hop must you forward that packet in order for the packet to make progress towards the destination. So that's forwarding, right? So you'll do that first week. So we're using static routing. We actually provide the routing table using command line or something like that. You'll get the details. Second week of this assignment, you'll implement the routing algorithm. We'll give you the topology. We'll give you a graph, basically. We'll have a bunch of a list of nodes and the edges between them. There'll be a specified format. So you'll have a graph, and you'll need to implement one of the distance vector routing protocols. It's a combination of using a combination of these two components. We have a router that can not only discover changes in the topology, but also forward the packets. So that's the preview for homework 7. The reason why it's taking a little bit of time is I'm going to provide most of the code for drivers, libraries, and so on and so forth, so that you can focus on the networking code. Examples are, let's say, I said I'll give you a graph in a file, and you need to read that, right? I'm going to give you that code so that you can focus on the networking part. So one thing that we need to do is think about port assignments, and I'll explain to you why. So let's say we have a topology with 20 nodes. Right? So we're going to simulate that using 20 different processes. All right? And we're going to tell one of the nodes, okay, here's a packet and here's the destination. And that node will have to determine the next process to which it should send that packet. So that means all of these processes are listening on a well-known port number, right? Let's say you want to be able to experiment with a network with 20 nodes. How many ports do you need? You need 20 at least, right? But how many ports were you assigned? Two. Okay, so we have a problem, don't we? Okay. So just wanted to ask, who does the assignments entirely on Bayou, and who does it? You do it entirely on Bayou. Okay. So anybody else? Just the three. So most of you, how do you do your assignments?
Ubuntu.
You do Ubuntu on your laptop. I see.
Well, in between laptop and desktop.
Okay, in between laptop and desktop. Anybody else? This is an important discussion here. Okay, so you did. So who does the assignment? For example, you're not going to be able to do this assignment in Bio unless you have additional ports. That's why we're having this discussion, right? So can you raise your hand if you think you can do the entirety of your assignment on your personal machine that you already have set up? Okay. So we have at least 1, 2, 3, 4, 5. So you also use Bio?
Yeah, I go back and forth. I do some on mine and then test and work on Bio.
Okay, so we have at least five of us need some additional ports anyway. So what we will do is do port assignments. Earlier we had port numbers ranging from 20,001 through 20,000 something, depending on who is still in the class. We did port assignments when we had lots of students in the class. So that is what we had. So that's not going to be enough. Can you suggest to me a way to assign port numbers? So here's the range. Actually, I'll just do it here on the whiteboard. So earlier we had port numbers. So earlier we had port numbers. Hope you can see it.
I know you have one here.
Yeah, I have some.
I have some.
Yeah. That's only 2,000, right? So you basically have port numbers, 1, 2, let's grab that range. So we're allowed to use port numbers 20,000 through 21,000. So how should we assign these port numbers?
So you should leave the same last digit, but now do 20,101, 20,102.
That's a very reasonable suggestion.
Easy
So
for people to remember.
okay, so does everyone know the port numbers you're allowed to use now? Any questions? So let me just repeat that. So earlier, let's say your port number was 20, 0, let's say XX. Okay, so this is the type of port numbers you had. So you're allowed to use, let's say you had AB, you're allowed to use XAB.
What's X then? How do we know what X is? Any of them?
Any digit, yeah. So how many pores do you have now?
Oh yeah, we'll have exactly
10. No, 10.
No.
No, because you already
You
have
should have gotten 2 in your
Oh,
first.
so
You should have gotten 2 in your first.
So this is 20, right?
Oh.
How about this? We can also, can we use this? Can we put an X here?
Yeah.
Well, you said
We could do
21K.
0, 1.
you said up to 21,000.
Yeah, but
Yeah. That's it. So you're allowed to use these port numbers. Just check it out. 20X AB. Okay.
All right. Any questions on the general idea of this assignment? Of course, the details you don't have it yet. So hopefully it'll be less painful than others. That's kind of the goal. All right. Let's start talking about where we left off last time. It's easier to abstract a network as a graph when we are thinking about routing algorithms. So each node here is a host or a router, most of the time a router, right? And we've been discussing how to find routes between two nodes in this graph. And if you already took basic algorithms or discrete math type class, you already know how to use shortest path algorithm. The only difference is we're doing a distributed version of that. Right? When we started shortest path algorithm, we were given two things. What are they? G equal to V comma E. Is that the notation that you guys use? Yeah, okay. So that means you know the entire graph. But when we're thinking about a routing protocol, especially distance vector routing protocol, we don't know the entire graph. This is a distributed system, so that's the difference. Keep that in mind. We finished discussing the basic distance vector routing protocol last time. It basically requires only the local state. What does that mean, local state? You only need information from your neighbors. You don't need to know the entire network. Why do we care about this? Local versus global state. Yeah. But what if the network is dynamic? Why is that a problem when we're talking about local versus global state?
Because keeping track of global state or dynamic network is a lot of work.
Yeah, keeping track of global state in a dynamic network is a lot of work, because if something changes in the network, then you have to propagate that information to everyone in the network. Right? But more fundamentally, if you have a large network, it's just hard to keep track of all of that information in a central place. Right? But we have this other type of routing protocol called link state protocol, which actually requires that you need a global view of the network. So you can already sort of guess which algorithm might scale in certain ways, in certain aspects than the other, right? Okay. So each node is going to maintain that 3-tuple, destination, cost, and next up. Again, we already discussed this last time, just as a refresher. And when you send an update to your neighbors, you're going to send, okay, I can reach this destination with this cost. So that's the message that you're sending to your neighbors. And why are you sending this message to your neighbors? So that the neighbors can discover this alternate path, if this is an alternate path. Or if this is the best path to a given destination, your neighbors ought to know that the best path to the destination goes through you, right? And here's an example we also discussed extensively in the last lecture. Which one of these tables do you advertise to your neighbors in a distance vector routing protocol?
The one on the bottom left.
The one on the bottom left. So this table on the bottom left it says, so this is B's routing table. It says from B, the distance to node A is 4, or cost. I might use those two words interchangeably. The distance to node D is 1. That's what that table says. Distance vector routing protocol allows you to compute this table. We said the routing, these routing protocols help these nodes compute the best path to the destination. But there is only one path to the destination. Why is that? That's what we said, right? That's the point of routing protocol. You have many possible paths from one node to another node in the network, and this distance vector routing protocol is supposed to let you compute the best path to the destination. But we only have one path here. Why is that? Why just one? Yeah, so the protocol has already computed the best path, and here's the best path. And how did we compute this best path? That was the previous slide. Update local table if we received a route that is better than the one that we already have. What is this process called in the context of shortest path algorithm? I think you might have used a technical name to describe that process when you compute the shortest path. So there's initialization, and what's the next phase? Okay, it's your job to find out, okay, what it's called. Sometimes it's nice to know the technical words to describe the process. Helps in communication. And at the end of last lecture, we started talking about how to propagate failures. Why do we need to propagate failures? Why do we even care about failures? Well, we don't want network outages, right? Okay. So whenever there is an outage, we want to be able to route around it. What's the common story we hear about? Was one of the reasons why the internet was designed. It has to do with wars.
Disrupting communications is like the first thing you want to do to your new tablet.
Yeah, and it's supposed to survive what? The internet.
Oh, nuclear.
Okay. So that's what we commonly hear about, right? So how can the internet survive these severe disruptions?
By routing around.
Right, by routing around these broken links. So in the context of this particular algorithm, we're not talking about internet scale routing, but the same property is desirable even in smaller networks. So let's say this particular link, FG, breaks for whatever reason. We need to propagate this information somehow across the network, right? But in distance vector routing protocol, is there a provision to tell everyone, okay, this link FG failed? No. So what's the only thing that we're allowed to advertise?
The time.
Not the time.
Oh yeah, sorry.
Yeah. For a given destination, what is the cost? Or what is the distance, right? So what F could do is it could set the distance to G to be infinity, a large number. And it can advertise to its neighbor. Who is F's neighbor right now? A, okay. Good. So it can tell A that my new distance to G is infinity. Just a quick note on the notation. So do you see a 3 tuple right next to A? Destination is G. Distance is 2. And next hop is F. All right?
What's the directional arrows versus...
That's the path. It's the path. For example, look at E. Who is the next hop?
A.
Yeah, for destination G. We're just talking about one destination just to make the discussion easier. Why is the second number or second element of that 3 tuple 3 right next to E?
Sum of the two.
Yeah, it's 1 from F, 2 from A, and then if you're going through A, it's going to be 3, right? So when A receives this message, what will A do?
They'll broadcast it, that same thing, wouldn't it?
So yeah, it says, okay, well, my route to G goes through F, but F said it's infinity, so. All right. It says, okay, I'm in trouble. We said that these routing protocols send periodic updates every 10 seconds, every 30 seconds, or something like that, right? Let's say C sent an update. So what does that update contain? Just two things.
The destination and the cost.
Okay, what's the destination? G. Cost? 2. Okay. So it says, okay, my route is in trouble, and it received this message saying, there is a node in the network that claims to have a path to G with cost how much?
2.
Okay. So what should A do?
Calculate its cost to that node and add it to the cost of
And what's the answer?
G3 broadcast.
Okay. So it'll say, okay, I can go to G at cost 3. Okay. Good. Now, what is A going to advertise? 2 things.
G and 3.
G and 3. And which nodes will receive that advertisement?
F and B.
F and B. Okay. Let's think about node F for a moment. So F knows that FG is broken, but F received an advertisement from A that said G3. What should it do?
Update its table that says where the next hop
So
is.
who is going to be next? Next hop?
A
A is going to be next hop. And what is the cost?
4.
Okay, good. Same graph, different scenario. In this scenario, link from A to E fails. So A is going to advertise a distance of infinity because the link just broke. Now, B receives this advertisement sent by A saying it's infinity, but it remembers that there is a path to E through C. It's longer, it's 2 hops, but that's better than infinity. So B decides it can reach E in 3 hops. Now, B is going to advertise this path to E, saying, okay, I'm 3 hops away. When A receives this message, it realizes that the direct link is broken, but it seems like there is a path going to E through B. It's longer. It's 3 hops from B, so that means it's going to be 4 hops from itself, but that's better than infinity. So it's going to say, okay, I am 4 hops away from E, and it's going to advertise this path. C receives this advertisement and says, okay, it's E is 5 hops away. When does this stop? Turns out you can go in this cycle for a while. So if you get confused, I'll post this video and you can look at it again until you're convinced that there is such a loop. Okay. In general, when you have that kind of triangle and a route sticking out, it's very easy to come up with an example to say, okay, you get this kind of count to infinity problem. So this is called count to infinity because the cost will keep on increasing. We showed how it goes from 2 to 3 to 4 to 5, right? It can actually continue to go up. All right. And any questions about this problem? Why is this problem happening?
Because it's just, they're continuously broadcasting that I have a connection to this, but since it has two things that are basing that on that broadcast, it just goes in a circle of updating every single time.
Yep.
It says, oh, well, you have it in 3 hops, that's cheaper than this
Infinity,
4 hop,
for example.
or yeah, this infinite, and then it says, okay,
Yeah.
well, then mine is 4, and
Yeah.
then the broadcast says, well, that's better than infinite, so I have this many hops, and it just keeps going up.
Yeah. All right. So here are the basic emergent properties of this algorithm. Good news travels fast. What is good news in the context of routing? It's usually there is no link and you have a new link that's going to connect 2 different parts of the network with something shorter than earlier. That's good news, right? Another good news is a link that had high cost or long distance suddenly becomes shorter. So that's good news. It turns out it's pretty easy to propagate this information across the network. For example, let's say we have node A, and link AB has cost of 4, and it goes down to 1. And if you receive that, it's a no-brainer. You should use that path, right? How long does it take for this kind of message to propagate across the network? The answer is down there. What does that mean? Let's try to understand that. So let's say we have a network where all the nodes are connected to each other. Everything is 1 hop. How long does it take?
I don't know what diameter means in terms of the graph.
Number of edges.
Max number of edges.
Yes.
You need to get from any given point to other.
Yeah. If you compute the shortest path between each pair of node in the graph, and you take the longest of that shortest path, that would be the diameter. So if you have a long network, it's going to take a long time to propagate this message. If you have a short network, it's not going to take as long, right? But bad news can travel slowly. And we already looked at an example of bad news in the previous slide, right? So there is no need to get terribly confused here. So what are examples of bad news?
A link going down or a node's cost increase.
Yes.
Or a node disappearing.
Yeah. So if we think about count to infinity, for example, like we discussed here, how long did it take for the bad news to propagate across the network?
Infinitely long.
Yeah, it took a long time, right? Okay. All right. Now we know that these routing protocols can sometimes give you loops. How can you get loops? I guess you were asking that question, right? How might you get a loop here? Just think of information that is not synchronized, right? So let's say you need to send a packet from A, let's say from B to A. Before the link went down, or sorry, we can just say, for example, you need to send a packet from let's see, yeah, B to A. We can think of it as B to A. How should B send that packet to A? Send B to A, right? And let's say node C. Let's say if C were ever to receive a packet with A as the destination, where should C forward that packet?
B.
To B, okay. Let's say the link cost went up. So B knows about it, right? So how should B forward that packet? B has a packet that it needs to send towards A.
Send it back. It's going to send it back to C.
It needs to send it to C because that's shorter, right?
And C is going to send it to B if it doesn't know that the cost to A went
Yeah,
up.
it doesn't know right now. So C is going to send that packet back to B.
Will it ever know it's we'll see every now and then because we play right now.
Oh, it might eventually propagate. It might eventually propagate. But does everyone understand this loop? Okay. So this is a...
This is not an infinite loop.
Yeah. So infinite loop is something that happens on the control plane, or count to infinity. Sorry, not infinite loop, count to infinity. Right. So there we're just trying to compute the topology.
We have
Here,
two kinds of.
this is happening on the data plane. What's data plane? It's the part of the system that is forwarding the packet, right? So the topology is set. It's inconsistent. All the nodes are doing is looking at the table. Destination A, what's the next hop? Destination A, what's the next hop? So are you convinced of this loop in the data plane? Okay. So these are two different types of problems, okay? Let's keep that distinction clear. All right, how do we avoid loops? All right, any ideas?
Not allowed to send something back from where it came.
Yeah, so let's just think about data plane. So how do you prevent data plane loops? Yeah, so you don't forward the packet to the same node. But let's say, imagine a more complex topology where the loop is of size greater than 2. How would you modify your algorithm?
Maybe, I mean, I don't know, but I would maybe keep like a buffer of recently sent packets and just compare.
Let's say in that case, so the suggestion here was you keep a buffer of recently sent packets, and whenever you receive a packet, have I already forwarded it? If I have, drop it. That's your suggestion. But let's say you're forwarding millions of packets. Then it might be wasteful to keep this huge buffer.
We have to look for a solution that's good enough.
Yeah.
Some kind of, because you cannot really keep track of
all the packets, right?
Yeah, everything.
Yeah. So one of the things that you can do is, for example, when you're doing network programming, do you have the freedom to put stuff in the packet? Yeah, otherwise you wouldn't be able to send a message, right? So what you could do is on the packet, you can include a counter. Every time you forward a packet, you increment the value of this counter. So let's say, we are programming a forwarding engine. You receive a packet, look up the value of the counter, add 1 to it, write it back to the packet, forward it. If there is a loop, what happens to this counter?
It's really big.
It's really big, right? So even if you have a loop of size 5, you can still detect that there's something funny going on here. So if you want to use that technique, you need to know what is the right value. How do you determine that?
Size of the network.
Well, what's the size of the network?
Oh,
Yes.
if you're on the internet, you
Can't
compute every single node on the internet and there you go.
We're talking about the distance, first of all, not the billions of nodes, right? The distance between one
How many
node.
hops?
How many hops, exactly. But what number are you going to put there? Give me a number.
32.
32, okay. But what if I have a network that's 35 hops? What's the problem?
Start getting a lot of packet drops.
Yeah, you start getting a lot of packet drops because the logic in our forwarding engine says if this counter, called TTL, for historical reasons, it stands for time to live, but it's actually a counter. So the logic in our forwarding engine says if TTL is greater than 32 in your case, drop the packet. So that's clearly a bad thing if we have a network that's larger than what we expect.
This limit, the TTL thing is not constant.
It's
so if you see a lot of drops, maybe double it in size and see if you get less drops.
Okay. But TTL is set by the source.
Yeah.
So actually what happens is not that you increment. The source actually says, okay, I guess the network is, 20 hops, and then you keep on decrementing that. Anyways, you get the idea though. The challenge here is, how do you set that threshold? But if you want to go for a solution that works, 95% of the time, as long as you set a reasonably large threshold, you'll be fine. Okay? Does it repair the loop? No? It doesn't? Okay, yeah, it actually does not. It's just that we're preventing the packets from swirling, in the network. That's all we're doing, right?
But can't you then detect that you're on a loop?
Yeah, you could potentially use that as a, if you can potentially use large TTL values if it is an incrementing counter, or if it is a decrementing counter, 0 potentially, as a signal that there is something wrong with the topology. And why might you want to do that?
So you can send out a special update saying, hey guys, we've got a loop, like synchronous.
Yeah, or there is some problem, so you could send an update across the network or relevant nodes that we have a problem in the topology. Let's try to discover the topology or recompute the routes. So how about count to infinity? That's a loop in the control plane, right? Not necessarily data packets are going round and round. It's just that the paths point. If you follow the path, you're forming a loop. That's what's happening in the control plane. But it turns out, if you set a small cost to be infinity, and after a while the nodes will say, well, we have a path of length infinity, so that's not a valid path. Because the cost is going to keep on increasing, right? A better loop avoidance might be to use these techniques. The first one is called split horizon. The idea is when you're sending an update to a node, you don't include the route that you learned from that node. If we look back in the earlier example, yeah, here. B and C learned the route to G through which node? From A, right?
I think you want the other
Yeah.
example, right?
Right.
This isn't the count to infinity example.
Yeah, so here. So it's actually very similar. So B and C first learned the route to E from A, right? So when B and C advertise the route, if they don't include the route that they learned from A, then we wouldn't have this problem. But only on the advertisement that they send to A. So does this make sense intuitively? So what we're saying is B learned that there's a way to get to E through A. So A advertised saying, okay, B, you can get to E through me. That's what A said, right? But later, does it make sense for B to actually advertise to A saying, oh, there is a route that route to E through me? Does it make sense for B to say that?
Not for A.
Yeah, but that's what was happening earlier, right? So that's the idea behind that's the idea called split horizon.
But A advertises distance in terms of time, right?
No, in terms of some metric or cost.
Metric, but B advertises in terms of hops, right?
No, everyone advertises in terms of hops. So A says, I'm 1 hop away from E. And based on that advertisement, B knows that it is how many hops away? 2, right?
Well,
So
why don't A just later, when it loses contact with E, say, I'm 0 hops away from E, and you
that'd be even worse, right?
No,
then
maybe,
it's,
but you
Great, 0 hops,
but
that
you-
means you're E. I can just
no, but you
send
agree
directly
on.
to you.
yeah.
Oh, wait, but you agree on
Uh-huh.
that obviously you cannot be 0 hops away.
Yeah,
You can-
so let's say, but
you
you're
can be
saying-
1 hop. So you say if somebody says I'm 0 hops away, that means
Yeah.
you have no contact with it. So we might.
Okay, so you have no contact, right? So now B is going to advertise saying, I'm 2 hops away. And then A is going to say, oh, okay, there's an alternate path to E. That's 2 hops. Does that make sense?
You're just replacing infinity with 0. The same thing still happens. You're still updating each other.
Let me explain that again. So A says, I'm 1 hop away from E, right? And B says, okay, great. I'm 2 hops away,
Oh,
right? And when this path A fails, A still receives this advertisement from B saying, I'm 2 hops away. So what should A do?
I'm 3 hops away.
Yeah, exactly. So A said, oh, okay, so this direct path failed, but it seems like there's an alternate path that'll allow me to get to E using the slightly longer path. Does that make sense? So the idea called split horizon prevents us from getting into this situation. And how is that? B is not going to advertise to A saying I'm 2 hops away because it actually learned about that path from A. B might still advertise that path to somebody else, but not to A. And there's a little addition called poison reverse. And the idea is you explicitly include the cost of infinity when you advertise that route. So when B advertises cost to A, it'll say the cost is infinity. Earlier it was implicit, it just didn't advertise the route. And if you think about why this makes sense, I can actually send you pointers to it. It is helpful a little bit. In certain cases, it helps the network converge faster. You'll actually implement split horizon with poison reverse in the assignment, because that's kind of the fundamental thing about distance vector routing. But it turns out it doesn't solve all the problems. You can still get loops, especially if you have larger network, larger loops. So this idea behind split horizon is you don't advertise the same route to the node that advertises, but if you have a larger loop, this idea is not going to help you. But most of the loops, if they are short, this will get you most of the way. The other class of routing protocol, they're called link state routing. The idea is you send to all the nodes in the network information about your neighbors. And this packet that you're sending it to all the nodes, it's called link state packet. It has the ID of the sending node and cost of link to each directly connected neighbor. And sequence number, time to live. Yeah.
The cost of the link to each directing neighbor from the source. So just those.
Yeah.
If you're connected to 2 neighbors, then you only send that for your 2 neighbors.
Yeah, to everyone though. Yeah. But just your 2 neighbors, that's it. That packet is just going to have information about these 2 neighbors. How is this different from distance vector routing in terms of information that you're sending? In distance vector routing, what is the information you're sending to who? So you're sending information to who in distance? To all your neighbors. You're sending information to
All the nodes about your neighbors.
all the nodes about your neighbors in link state routing. See the difference? So you need to flood this information reliably to all the nodes, because all the nodes need to get this information. So at the end of this process, what does each node in the network have after you run link state routing protocol?
Complete map.
Complete map of the network. Is everyone convinced that each node will have the complete map? So basically, each node is going to collect information about its neighbors. Okay, I'm node A, my neighbors are B, C, and D. I'm going to put that in a packet and send it to all the nodes in the network. When all the nodes do the same thing, each node has a map of the entire network. You have a graph that represents the entire network. Then how do you do routing if you have a map of the entire network? Then you go back to your data structures class, right? If I give you a graph, say, okay, here are all the nodes, here are all the edges, you just run Dijkstra's shortest path algorithm at that point. Yeah, we don't need to go through the details of Dijkstra's algorithm because you guys already know it. So there's just one small piece remaining about link state routing. So you run Dijkstra's algorithm, and what is the output of that algorithm?
Short path between 2 nodes.
Say that again?
Shortest path is get to whoever node you specify.
Yeah, so each node is going to know for a given destination what is the shortest path, or the parent pointer, or whatever you call it, right? What's the next hop? So that's the control plane story. So now let's think about forwarding using link state routing. Can you tell me how it might work?
You just include the path that you want to send it on whenever you send the packet.
You don't even need to do that, right?
You don't even need to do that. You just need to calculate next
Well, I
time.
guess,
Because
since everyone's already
whoever
kind
you're
of
sending it
calculated.
to also knows.
Yeah. So you have the entire map of the network, and you can actually pre-compute what the next hop should be for each destination. You keep that in a table, and when you receive a packet, look up the destination. What's the destination? D. Go to this table. For destination D, the best next hop is, let's say, B, and you just forward it to B. Okay? So in the control plane, we collect information about all of our neighbors and flood it reliably across the network. And at the end, all the nodes will have the entire map, the complete map of the network. And you can run Dijkstra's algorithm ahead of time. In the data plane, when you receive a packet, you look up what the destination is, you consult your map or the shortest path table or the routing table, and you find the next hop, and you just forward it to that node. Let's think about some of these examples. Not example, some of the properties of these two routing protocols. So how many messages do you need to send in distance vector versus link state routing? Let's think about distance vector first.
One per neighbor.
Yeah, if you have n nodes, you need to send how many messages? N, right? Because you need to send messages to all the nodes. How about for link state?
You're going to have to send it your number of neighbors times the number of nodes that you have to send it to.
Yeah. You need to send a lot of messages, a lot more than distance vector.
I don't understand why you have to multiply those two together.
So let's say you have let's say each node, let's say we have 10 nodes, and each node has a degree, let's say 3. What's the total number of messages you might have to exchange? What's the first thing that you need to do? What's the first thing that you need to do? Each node.
Calculate distance to its neighbors.
Is that free? That's not free, right?
So they've got
And
the number of neighbors.
when you send a message to a given node, what needs to happen from that point on? Let's say that node has D neighbors again.
Again,
This is the same process, so it's the neighbor.
Yeah, so it needs to send this message to all the neighbors, right? Because we're trying to send this message to all the nodes in the network. All right.
So this only works if you have the same degree for every node.
No, so this is an asymptotic analysis. Yeah. Let's say roughly you have degree D and n nodes, and what's the number of messages? Just think of it that way.
Is that the way it's going to be in our homework?
In our homework, we'll have concrete numbers. I'll give you a concrete topology. Yeah. All right, so we'll just leave most of that discussion just on the slide. If you have questions, please ask me maybe next class or on the discussion board. I'll just give you 2 examples of the type of protocols that we talked about. RIP, it's a distance vector routing protocol that's actually used. And there's another protocol called OSPF, that's a link state routing protocol. Now, you'll implement a version of RIP, or something that looks like RIP.
Yeah, that one's a little bit more complicated. 244 pages versus 30.
You know what RFCs are, right? These are publicly available documents that describe how certain protocols work, or what's the packet format, and so forth. If you go to Google and just type RFC 2453, you'll be able to read the descriptions. So in a distance vector routing protocol, what's the information that we need to send? I mean, this is just some basic information about RIP. You can just read there. I don't need to repeat that. But what's the information that you need to send in distance vector?
To your neighbors.
Yeah. So basically, you need to send information about next hop. So this is what the packet looks like. Did we learn how to read diagram like this? I think in the beginning we did. Yeah, good. So this is the header, and then there is RIP entries, and each entry looks like that. Why do we have multiple entries?
Number of neighbors.
Yeah, we might have large number of neighbors. So you have IP address, subnet mask, what's the next hop, metric. We don't need to send next hop, do we? In distance vector routing protocol? This should be enough. Why do we have it here?
You have to send the next hop, don't you? Oh, no.
He's just saying, okay, here's the destination, here's the cost, right? Why do we have this? I'll let you read this. So the basic idea is, if you have a set of routers, but if some of them don't have this protocol called RIP, you still want other routers to be able to advertise what paths are reachable through that router. Does that make sense? That's why you need that next hop. Is that clear?
Is it like a cheap way of not implementing the link state protocol?
Or I would say, if you don't want to run this protocol on all the routers, then you can say, okay, to this destination, here's the best next hop. Because in distance vector routing protocol, you're only allowed to say the cost to the destination through the best path that goes through me is 5 or 10. That's the only thing you're allowed to say. But this next hop field allows you to advertise a little bit more. It allows you to say, okay, the best path to this particular destination is through this other router. And if that next hop address is 0, that means it's the standard distance vector message. We don't need to do the next hop in our assignment. There's a protocol called OSPF. Fortunately, we don't need to go through the details. It's a link state protocol. You collect the information about your neighbors and to other neighbors, run Dijkstra's algorithm to compute the shortest path. And there is a notion of areas. That's the terminology they use to group the routers. It helps you scale the protocol a little bit. So now, if I had to ask you to implement OSPF or RIP, you should be able to do that, right? Because you already know how to write network programs, right? You open a bunch of sockets, you send certain messages to your neighbors, do some computation, and send the result of computation to your other neighbors. And you'll be more confident after the next homework. All right. So even though we're running a little bit late, let's just take 1 minute break, and then we will start talking about interdomain routing. All right.
So neighbors and areas in OSPF, it treats distant regions as being a single node?
Yeah, that's the idea behind all these schemes.
I did the live review about the box.
Which box?
I want to steal a box.
I don't understand this box.
The box. We need a box. We have a very nice random box. We keep all your some of your electric devices.
Is it in the lab?
Yeah.
Really?
Yeah, it's like a research.
Is it mine or Larry's?
Yeah, well, it's yours and not so first you should ask home. Because we're going to go to drive to Home Depot to buy a cargo box and make a box. This is a very nice box. Yeah.
Oh, okay.
So stop after the class, see what's in the box.
I have no idea what's in the box.
Yes, check it out and see if I really
Okay.
don't, then we'll take it.
All right.
Because we need to, really connect thing.
Yeah.
We're trying to build something.
Yeah. Let's go there after the class. And then,
Homework. Okay.
Yeah, it'd be nice to only have to not have to come here, but I really will.
Yeah.
Still come here. At least like a couple days a week.
Yeah. And for the days we only, like, we just do it all the time. I really do want to attend it.
So you guys don't want to come to the class?
No,
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 we're
we're
taking
talking
break.
about.
Okay.
It's not really going to be much of a break.
Yeah. Well, you can pretend that the homework has not been posted.
It's due on Wednesday.
So we should
Yes.
just close our eyes and
Yeah, just
cover
close.
our ears.
You can work on it a little bit this week if you're already done with the previous one.
It's due next Wednesday after spring break. Homework
2
7.
weeks.
Nah, it's due on spring break.
Are you serious?
No.
It's due the Wednesday, the week we get back.
How does it take? Is it same longest to do it?
It'll be, I think, less work.
Are you serious?
Yes.
But that's what you say every time.
Oh, yeah, that's right. So let me just take 1 minute, and then you can. Yeah. Okay. Good. I was planning to cover a little bit more, but thanks for reminding me. All right. So we talked about 2 classes of routing protocols so far, right? But it turns out we use a completely different routing protocol in the wider internet. We talked about OSPF, for example. It's a link state routing protocol. What's the main challenge with link state routing protocol? Remember, you need to collect information about your neighbors and then send it to everyone, and you have the map of the entire network. Clearly, some scalability challenges. We use this protocol called BGP to route across the internet, across the organization, across the domains or autonomous systems that we talked about. Let's think about some major differences between how we should design routing protocols that we're running within an organization or smaller networks versus the wider internet. Let's think about this issue, trust. So if it is within an organization, there is more trust as to who is allowed to use that network, how much, et cetera, versus the wider internet, right? Different autonomous systems might have different policies in terms of what links are supposed to be used by what parties, what organizations, and finally, money, right? When we are sending packets just across, let's say, our university campus, we don't worry about money that much. Let's say when computer science department sets up the network, and let's say there's a lot of traffic between computer science department and, let's say, business school, they don't start negotiating with each other, saying, okay, you're sending a lot of traffic that we're sending to you, so you need to give us more money, et cetera, et cetera. But in the internet, that is certainly an issue. So those are the reasons that motivate the design of a routing protocol that allows you to route based on policies. Okay? Not just based on cost, not just based on, okay, this is the best path from this point to another point, but based on policy, based on business decisions, sometimes based on political decisions. Any questions about why the previous routing protocols might not be the best one? At least the high-level motivation? Okay, it seems like we understand that, right? So when is shortest path not the thing that you want to do in the internet?
When it costs more money.
Say that again?
When it costs more money.
Yeah, when it costs more money, right? So how do you put money into the equation? We need a routing protocol that allows us to express these policies. And that's what we're going to talk about in the next lecture.